Hello friends, my name is Vinay Pottigar and I welcome you all for this video tutorial which is based on theory of computation. So today we will be concentrating on the unit number 5, which is push down automata. So today's topic of discussion within this, we will elaborate the definition and the representation of a particular push down automata is. So just let's begin our discussion on this. So we'll start with the definition and representation of PDA. So PDA is a short form for push down automata. So in this, so the class of PDAs recognizes exactly the class of context free languages. So to prove a particular language as a context free language, I have two mechanisms. So two concepts I have to prove a particular language as a context free language. And one of them, which is write a particular context free grammar, which we have already discussed. Now today is we'll see how we can design a PDA moves to represent a context free languages. So in this mechanism, we'll just take a simple example first. Consider this example. So L1 is a particular language. So every string X within this, which is a composition of zeros and ones, has in this format. So 0 raised to n and 1 raised to n, where n is tends to infinity. So if you want to design a context free grammar, see, we'll just compare. If to prove this as a context free language, I have two concepts. One is context free grammar. So grammar consists of or fold tuples v sigma sp, where v is all certain non-terminals which exist into a particular grammar rules. Sigma is all input symbols. S is the starting alphabet of a grammar, where all the derivations of that string start, how the derivation starts with. And P are certain rules which exist to prove that this L1 is a context free language. In this 0 raised to n, 1 raised to n, where n tends to infinity, is achieved with these two grammar rules, where S is producing 0 as 1 or directly S is producing null. So in this context itself, so S can be derived null directly with its 0th iteration. If I wanted to go across multiple iterations, so S can be rewritten with this 0 S1, and this S is terminated by null, so we can generate 1 0 1 1. So if I wanted to go twice over this, so S can be replaced once by 0 S1. Again, this S can be replaced by 0 S1 using this context free grammar, and will achieve two zeros, two ones, which is 0 raised to 2, 1 raised to 2. Now these grammar rules are generative. So grammars are generating the strings of a particular language. So the 0 0 1 1, I could achieve this from the starting alphabet of S. So grammars are specifically said to be generative devices, where that what we are looking right now is to how to design a PDA to accept the same L1 language. So just take the representation first, what PDA actually means, what it composed of, and how it works. So idea of PDA is very simple. It comes with this basic elements. One, we have the input tab. So whatever input you wanted to provide, it can be given on this tab. So we have this particular finite state machine. So finite state, we need to design according to the problem statements, which will have the particular states, transitions, accepting state, a particular move of that FA, and on the input symbols that it will operate. So this head is a read-only head. It only reads from this input tape one character at a time, and once it reads this, the pointer moves ahead to read the next character. So this is read-only head. Now along with this finite state machine, I have one more element which we call it as a stack, which works on LIFO order, last in first out order, where this head which is pointing to the stack can update the stack or so stack operations we can perform based on this pointer, which is push operation or pop operation. So with this elements, see, we can design a particular PDA moves for the acceptance of this L1, which is 0 raised to n and 1 raised to n. See, according to the problem statement, so everything is logical. So designing a particular PDA moves, it's a logical process. So how many steps it will have, how many moves are recognized to the PDA through which the PDA can text its operations. We'll see it one by one. So basic mechanism is how to design this finite state machine and how to apply a particular logic to accept a particular string of a L using this stack. Now go across and just simply check how this L1 can be accepted with simple examples. Let's see if the input is 0, 0, 1, 1. Let's not talk about how to design this finite state machine first. So just elaborate with the paper and pen how this can be achieved, or how we can cross check the total number of zeros that are available on the input are equal to total number of ones within a particular input string, and which is in the same exact 0 raised to n and 1 raised to n pattern. So we won't thinking about this PF finite state machine, DFS or finite FA right now. So we have this input tape and we have this particular stack. So the condition number 1 is when your first input alphabet is 0, at that time this Z0 is which is a first stack alphabet which is available on your stack. So top of stack always points to this element which we call as Z0. So this is the condition number 1 where I'm reading a particular input. Nothing is on top of stack except this Z0. So if this condition is true, see, for every zero will be pushed one by one onto the stack unless we read a first one in this sequence. So condition number 1 is 0 we are pointing at that time, Z0 is on top of stack. If this condition meets, this 0 will be pushed onto the stack, and once you read this character, the head will point to the next input character which is available for being scanned on this input tape. Now check the condition second. Now my basic goal is unless and until all the zeros on my given input, unless and until it gets over, every element 0 will be pushed onto the stack. So this second is this is 0. If it is, I'm reading from the input tab, at that time if 0 is available on top of stack, so this arrow is pointing to the top of stack, still this 0 will be pushed onto the stack and the input head will point to the next alphabet. See, this will continue unless and until all the zeros will be pushed onto the stack one by one. So step number 1, step number 3 is where we stopped, where my pointer is pointing to 1 and top of the symbol is 0. Now if the 1 is appearing on your input and the corresponding 0 is available on top of stack, so this means we can count the total number of zeros pushed onto the stack against the total number of ones available on input sides. So based on this input element 1 on input tape, and at that time if 0 is available on top of stack, this 0 can be popped out of the stack. So this is what exactly has been done in step number 4. So after reading this one and popping this top of symbol 0, single 0 is left and next element will be the top of stack and the pointer is pointing to the next basic element 1. Now again we'll check back. If input is 1 and 0 is available on top of stack, we need to count this. The machine is counting against this one. If 0 is available on top of stack, we'll just pop this 0 out of the stack and making sure we are counting the total number of zeros and total number of ones, whether they are equal or not in the right order. So once this zero go out of the stack, only the element which is left on stack is Z0. Now check the condition, my input is exhausted and only the starting element of the stack is available on top of stack. So this is the condition for acceptance, where I'm reading null means the input is exhausted and at that time nothing is available on top of stack except Z0 from where we begin. So this is a condition of acceptance. Now we didn't think about how many state I will have in a finite state machine. We'll just go back and check all those moves right now. Now step number 6 is what is left on input. Null is left on top of stack and Z0 is available on top of stack. So this is the perfect, this condition is sufficient to identify 0 raised to n and 1 raised to n pattern, and this is the condition of acceptance of that particular pattern. Now look ahead how to design the moves and how many states will be there. So for this design of a particular push down automata, I think 2 states are sufficient. One is non-accepting state and second is an accepting state. So as for the logic which we applied through these steps, it will give us the idea to formalize a particular move of a particular DFA or PDA. You know what it means? See, first state is a non-accepting state which we represented at Q0, and second is an accepting state which is Q1, which is left to be written here. So this state is Q1 here. So according to the logic, what would be this? So this is see, both the PDA table and the state transition diagram both are same, one by one. If you receive a state chart diagram, we can convert this back to a PDA move tables, or you have a PDA moves given in the tables, it can be represented with the state chart diagrams. So we'll look at what are the elements which are present, design of a PDA moves. So we have how many number of moves are recognized by this PDA, what is my present state, what input I am reading, next is what is the available stack symbol at that time, and based on this information how my PDA is acting or reacting, which is specified as a single move of my machine. Now if you check on the first element itself, when we begin, see, this is my element 0 on input. At that time Z0 is on top of stack. See, except this nothing will be available. So we can think about how the string starts with. So string starts with is represented with this move number 1, where I am on this initial state Q0, which is a non-accepting state. And then being in Q0 state, if I receive 0 at that time, if the stack contains a Z0, means the stack is empty, it contains only the basic elements Z0 itself. So according to our logic, this 0 has to be pushed onto the stack the way we discussed. So this is the move which we take, the first move. If I am in Q0 state, if the character being read on the input is 0, at that time nothing except Z0 is on top of stack. So this 0 will be pushed onto the stack. So this is the representation of a particular move which we recognized as, from this present state it jumps over to the next state Q0, it retains its states by pushing this 0 on top of stack. So how it is represented? So first element is the next state of this machine, what it is, and 0 is pushed over the Z0. So this is what the first element or first move we write with respect to this logic. And this similar move is represented in the state chart diagram. So we are going across from Q0 to Q0, means a self loop is there. So at that time, what I am reading an input character 0, and what is available on top of stack, that is Z0 is okay. And what what is the the move that PDA is taking. So PDA is pushing this 0 over this Z0, and the top up stack will become pointing to this 0 again, which we explained just now. So top up stack is incremented by 1 and it is pointing to 0. This is the first move. Now if you check the second move of this case, where the input is 0, at that time if 0 is available on top of stack. So according to logic, what we said, unless and until all the zeros are over, we will push every 0 on top of stack. So with this notational system, we will design our second move of a machine, where being into Q0 state, if input being read is 0, at that time if 0 is available on top of stack, this 0 will be pushed onto the stack and represented something like this. And what would be your next state? I'll retain my state from Q0 to Q0. So this is a move number second which is represented. I'm moving back from Q0 to Q0, where my input is pointing to 0. At that time 0 is available on top of stack. If this condition holds true, this 0 is pushed onto the stack. Okay, and this will continue unless and until all the zeros are pushed over the stack. Okay, and the condition reads that will be the input is pointed by 1 and the corresponding 0 is available on top of stack to cross verify how many zeros can be cancelled out against the zeros which has been seen from on the input side. Now according to this, we'll design our step number 3, or design move of your PDA represents being in Q0. If the input appears or 1 appears on your input, at that time if stack contains a particular 0, then we can nullify or pop the available stack symbol from the stack, and will operate the pop moves and will go across from its Q0 state to Q0 state. Will means we retain the state. See, this is the step number. Once you reach the upward 1 on your input and 0 is on your stack, so this pop operation will be carried out, where null will be replaced and the top of stack will be pointed to the remaining 0, and the the head will move to read the next particular character, and this will continue till all ones are cancelled out against all zeros. So again this one will be cancelled out again, this 0, and nothing is left on top of stack. So we'll concentrate on this last step. According to this, the last step what we find out is, being in Q0, if my input get exhausted and nothing is left on top of stack, so this condition specifies that all the zeros gets cancelled out against all ones on the input which is available. So for the last symbol, we need this is an accepting condition, so we'll move back from this Q0 to Q1, where this Q1 is marked as accepting state. So when to move from Q0 to Q1? When the input is exhausted and Z0 is available on top of stack, then we won't update the particular stack. After retaining this Z0 on top of stack, we'll go to Q1 state, which is marked as accepting state. Now let me clarify what present state means. Present state is represented by Q. Input being scanned can be represented by sigma valid inputs. It with the combination of it can be null also. What stack symbol is represented by? The stack symbols are represented by the capital Greek letter gamma. And the last PDA moves, it contains a particular tuple. What the next state of the PDA is, or push down automata is, and it's a cross product of or power set of Q cross gamma star. So what the next state of the machine is, and what operations we are carrying out to replace top of stack. Either we will be pushing something on top of stack or popping the stack element. Now let's understand this representation. We have already understood, but just go over it once again. So this is a simple example. Being in Q0, if I have a transition, self transition, it represents from Q0 it is going back to Q0. Next state will be Q0. At that time, if 0 is on the input and Z0 is available on top of stack, what corresponding action the machine will take? Okay, so 0 is left over this, so by mistake, so 0 will be pushed over this stack. So this can be read as being Q0 state, 0 is available on the input. If Z0 is available on stack, what the corresponding move of a PDA? So this is represented by this table or with this state chart diagram. Now again, by elaborating this, how it is represented, the single move, how it is represented. So see, this delta represents a single move of my PDA, which contains 3 tuples. It is represented what my present state is, what input I am scanning over my input tape, and what at that time what is available on top of stack. Based on this 3 information, the machine takes its next move to either to retain the particular state, which can be a next state, and either to push something on top of stack or push or pop out something out of the stack. So this 0 is pushed onto the stack itself. Now this is a particular single move of a particular PDA is represented with this notational system. Now go back and check what the PDA definition is. So according to the textbooks, so a PDA is having 7 tuples. Okay, so see, before going across this definition, so this is how your PDA looks like, particular state chart diagrams, and which we represented as particular moves. And if the PDA follows this all steps, it will accept all the strings of 0 and 1 Now just go back and check the particular example with this notational system of PDA. See, definition consists of 7 tuples. So 5 tuples are similar with your finite automatas, that is Q, sigma, Q0, accepting state, and your transition function. See, these 5 elements are common. Which 2 new elements are get added? This capital gamma, which represents the stacks symbol, and this Z0 is a starting stack element. So if you look back to this definition, so Q, which is dependent how the total number of states I should have into this finite state machine. So these are finite state set of states. Sigma is on which input alphabets you work on this. Gamma is the finite set of stack alphabets. Q0 is represented as initial state of that machine, which is Q0 in this case. Z0 is the initial stack symbol, which is always available on top of stack. And you have one or many accepting state within the PDA. So A is a subset of Q. And with the previous discussion, how this single move is represented as, so Q is the current state of the machine, what input it is reading, input being scan, what you are reading, and according to this, what is currently available on top of stack. So according to this 3 information and applying a particular logic, it takes its next move, and it can be at a particular power set of, it can be any possible combination of this, a particular state and stack alphabet combination. So this is power set of Q as well as gamma star. So either we push something on top of stack or pop something out of the stack. So this PDA, design of a PDA, is capable enough to identify 0:1 and 1:1 pattern. I hope you understand what PDA is. It consists of 7 tuples as elaborated, and how to design a particular PDA moves it based on a particular logic, which language we are trying to accept. According to that, the total number of states, the total number of moves will differ in a corresponding PDA. And if we could design a particular PDA in this format, we are saying, which is capable of accepting all the strings of a particular L, we are saying that the language L is said to be context-free language. So we have seen two arguments. One is if I could write a context-free grammar, still that language is context-free language. And if we can, or we could design a particular PDA moves for accepting a particular strings, and then that language is said to be context-free language. I hope you understand this basic mechanisms of accepting a particular language with the help of PDA moves, and how to construct a particular moves according to the logic. Thank you. Thanks a lot.